the session. And so, Michel, I trust you to make something again very lively for this tutorial. So thank you again.
Great. Well, thanks. Yes, actually, I mean, it will be lively, but on this tutorial, you'll actually be able to do quite a bit on your own. And then every once in a while, about every 15 minutes or so, I'll go through the notebooks and maybe discuss a bit the results. So let me share my screen just to again show you a bit how to get to the notebooks for the tutorial. So I should be sharing my browser. I hope you see it. So the way to get to again, there's basically two options to get the
So may I
notebooks.
ask you a question? So
Sure.
this notebook will remain there also after the school, or it will expire?
No, I mean, I can surely keep them there, or find a way to.
Okay.
So they're on right now on my GitHub, and I'll definitely leave them here. There's a question whether this very web page here will remain, but if not, definitely the link to my GitHub will still have the tutorials. But
okay,
I can keep this at least for a month or so. I mean,
very good. Thank you very much.
Change this very quickly. Yeah, so again, to have this page, you can just connect to this link here on my webpage on GitHub. And there's two ways to get the notebooks. Either you install it locally, but then you need to also install the tricks library as well as the TTQMC solver, and you can follow instructions here. I hope you already tried, because if you start now, this is probably going to already take a fair part of the session. Otherwise, you can click on this link, which brings you to Binder, which has a prepared notebook with all the necessary libraries. This can take a bit of time, depending on how much traffic there's on the website. Well, see, this time it was pretty fast. And so what you get is basically a list here of different notebooks, and you can pretty much click on them and go in the right order. To avoid Binder disconnecting you, it is good to click on that first notebook here and execute the first cell. So you do that with, you probably know those Jupyter notebooks very well by now, with Shift-Enter. And this just keeps a bit of activity on the server so that you're not disconnected. And then you can really start with one notebook after the other. The first two here, number 1 and number 2, they're very general notebooks about introducing those Jupyter notebooks and how to do plots. I suppose many of you know this already. So if you're familiar with the Jupyter notebooks, just skip those, and you can directly go to the more to the ones that are related to the lecture, which start with number 3, green function, and so on. So if you go, for example, to green function, there's usually a bit of text trying to explain, especially their definitions. And we're relying on a library which is called Tricks, which is something I started developing some time ago now with Olivier Parcollet, who's based at CEA in Saclay. And it's a set of tools that also exist here in Python. So it appears as a Python library, which has many body objects that you can more easily manipulate. So for example, the library will provide green functions and things like that, that you can manipulate a bit more easily than if you had to do that using NumPy arrays directly. So you do this by importing the relevant libraries here from tricks.gf for green function. This is just something to prepare for plots. And then there's explanations on how to manipulate them. So basically the goal of this first notebook, green function, is basically to get you familiar with the conventions that we use to define green functions and so on, and to know the names of the different classes. So for example, if you want to create a green function in real frequency, this is this GF refrec. And then for all of these things, they come with options here where you specify the dimension of the green function, because in principle a green function can have blocks that are of size larger than 1. So you specify this by giving indices. And the window here just tells, because it's a real function, I mean, it's a green function in real frequencies, it tells that you consider frequencies between -3 and 3, and so on and so forth. And so hopefully this notebook can give you a bit of an idea of how to construct these different green functions. For example, if you want to define them like this, there's the corresponding code here. And you can also then manipulate them, invert them, and so on and so forth, and plot them to see the results. So that's an opportunity to both learn a bit how to manipulate them within the Twix library, but then also to get familiar with the green functions themselves. If you're not very used to them, that's an opportunity to actually see it. That's when it's really when one gets his hands dirty that one really learns about something. So you've seen expressions like this before, but now you'll actually look at them. I think that's quite useful. Okay, and then at the end of the notebooks, there's in general a bunch of exercises to sort of see if you know how to manipulate the objects and so on. And this is true for all other notebooks. So the number 3, this one is really about just manipulating the green functions. There's not too much physics in there. There's one here, the 4, that you can almost skip, but it's about how to save your data in an archive. And then the things really start with 5 here, where we'll solve a first DMFT equation and try to study the Mott transition. So that's where the serious things start. And at that level, we're not solving the DMFT or the impurity solver within DMFT exactly, but we use something which is called IPT, which is basically second order perturbation theory. It's not exact, but it's quite fast. And because it's essentially analytical, we can, in this case, perform the analytical continuation that I was talking about, which is difficult to go from the Matsubara frequencies to the real axis to see the spectral function. So this can be done with this semi-analytical method here, and this will allow us to actually see the spectral function as we go through the Mott transition. And then we can go further, use the CT-int quantum impurity solver and solve the problem exactly and study the Mott transition in the Bethe lattice. So, just go one after the other. One thing that I need to mention, I mentioned that the other day, if you make modifications and save your notebook, it will be saved. If I save it now, it will be saved on the remote website. But if you close the session and go back, every time it reinitializes a new session from 0, and you will lose your notebooks. So if you want to keep a copy of your notebooks, go to File and download your notebook as a notebook, download as notebook, and save your notebook locally. If you want to recover it later on, you can go back to a new session, but then you need to upload those notebooks that you've modified. You do that with upload, and you can get the notebook, upload it. And obviously, if the notebook has the same name as an existing file, you have to overwrite it. And now you again have the notebook that you had. But you need to think about saving this quite often, because otherwise, if you close your browser, you may lose what you've been doing. All right. So there's exercises in these notebooks, and you can find the solutions in this folder solution. So these are the same notebooks, but in which the solution part has been filled in. So if I go to the very end on this one, for example, for green function, there's the exercise, but this time there's also the solution. So if you're stuck, if you want to see how this is done, just go to the solutions and try to understand the solution that are written here. And on my side, more or less every 15 minutes or so, I'll talk again and go through those solutions to discuss them with you. And at any time, if you have questions, well, just raise your hand or speak up. And I think all the questions are generally useful for everyone, so it's fine if we share this between all of us. All right, any questions so far? Okay.
So may I ask a question? How are we going to organize now a lesson? So we step by step go through all the notebooks, and then how we are going to synchronize with you?
Oh, I will go one after the other. So you know, everybody will go at a different pace. Some of you will be quicker and will be done, or maybe have already started looking at those notebooks before. So you know, basically, it's going to be hard to synchronize. But I'll basically every 15 minutes, I'll go to the solution of notebook 3, and then 5, 6, 7, 8. So you know, at that moment, if you're further ahead, you can either come back and look at the solution altogether, or just move on if you had no problems and go to the next notebooks. All right. Well, then I suppose I'll see you in about maybe 10 minutes or so to discuss this first notebook about green functions.
Michel, are you here?
I am.
I have a very simple question. I opened the Introducing Jupyter Notebook, lesson 1, and there is example of simple loop.
Yes.
So I want to, okay, when I run this loop, it gives me I equal to blah, 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 x equal to blah, blah, blah. How can I plot them in the same line? How can I print them in the same line?
Okay, so so I'll show you this directly on the screen. So here you want to have I and X on the same line. Is that what you want?
Yes, yes.
Yeah. So you would modify the print. Instead of writing it like this, you can print I is equal to I, and then one more comma, X is equal to X. And so that would basically do the job.
Okay, okay, thanks.
No worries.
Hi, I have a small question. Can I proceed?
Yes.
Yeah. So in the notebook on Green's functions, the example 2, impurity in a bath, could you please explain what exactly the function flat does? So as I understand it, it's replacing that summation which is there over k, sum over k, over all the states.
Are we talking
Right.
about this one?
Yes, flat 1.5, yes.
Yeah, so flat 1.5, this is itself, if you want, a green function, and this is the green function for a bath that would be flat. It's called a Wilson bath. It's a bath that is equal to a constant between minus 1.5 and plus 1.5 in this example, and it's 0 beyond it. And you can compute analytically, in principle, what the green function for this is. And this is what this function does. So this, if you want, returns a green function for that. So it's directly substitutes this delta here. So what this line does here, it fills the green function small g with the formula inverse of, so basically 1 over omega minus epsilon d minus v squared, and flat will be this delta here. So you have to think of this as a function of omega if you want.
Right. But the expression actually has a summation over all the Green's function, right? I mean, how do you replace? So the actual expression would be something like 1 over omega minus the epsilon d minus some summation over k, which is the self energy term, right?
It would be, in that case, it would be something like some, if you wanted to write it as a sum, it would be some sum over k of some vk, but all the vk's are equal to v squared. So this is why this came out here. Of 1 divided by omega minus the corresponding epsilon k that lead to a flat dispersion. And this sum is hidden in this, if you want. It's been carried, this sum has been carried out analytically, and it is inside flat.
Yeah, I'm actually having difficulty making that connection, how those two are connected.
I mean, okay, let me try to write this as an equation here. But if you want, you have this flat or the delta function of omega has an analytical expression. It's like you say, it's something like sum over k, but you can also see it as an integral over energies. of, and I'll try to write it, of the density of states of I omega, sorry, it takes a bit of time, minus epsilon. So
Okay.
that's the general formula. I've replaced the sum over k by an integral over epsilon. Rho is actually constant in the case of a flat bath. And this integral, this is something I can do analytically, and this is what's inside flat.
Okay, okay, I see. Okay.
Of course, you
Thank
you cannot do this analytically for any density of state rho, but in some
Right.
special cases, like the flat bath or even the semicircular, this integral can be done analytically.
Okay, thank you.
No worries. Okay. So I'll maybe go through the solution of this notebook about green functions. I know you're all going at different speeds, so it's of course tough to follow what you're all doing. If you've been there before and are further in the notebooks, just continue working, no problems. So a first exercise is to try to define a function, a green function, which has this structure. So physically, what this is describing is a green function of an impurity connected to a bath. So this is why it has two. It's a 2 by 2. One line is for the impurity and the other one for the bath. This omega minus epsilon d sort of describes the impurity level at energy epsilon d. This gamma minus 1 is a description of a flat bath here. And the two are connected via a hopping term, which allows for the electron to jump back and forth from the impurity into the bath. So you can define this by defining a real frequency green function. You fill the different components, the impurity, the hybridization terms, and the bath, like this. You invert it to get this green function, and then you can plot it. And actually, I don't plot the green function. I plot minus 1 over pi, the imaginary part of the green function. And you probably remember that minus 1 over pi of the real part of g is its spectral function. So what I'm plotting here is the spectral function for the impurity green function in blue and for the bath in yellow. And so what you see is a resonance at the impurity level, which is more or less sitting at the energy of the impurity level, which is 0.3. And you see if the V, if there was no connection between the impurity and the bath, this would be a delta peak, as we discussed. But because there's a scattering process that lets the electrons go back and forth into the bath, they acquire a finite lifetime, and this is translated by a broadening of this delta peak, and this is why this is broadened. And the broadening here is something that is related to the lifetime of the excitation. So the smaller the broadening, the longer the lifetime. From the point of view of the bath, the fact that now the electrons in the bath have a chance to hop on the impurity, this creates sort of a counter effect in the bath, and you see a dip in the density of states. Originally, this was a flat bath, so it was just a flat function, and now it has a dip exactly at that energy. Now that exercise is to connect and just to the green function of a free particle. So maybe you remember, but a green function that goes like 1 over I omega n minus epsilon, or 1 over omega minus epsilon, is just the green function for a free fermion with energy epsilon. And so what is n? What is the occupation for a level at energy epsilon for a free system, or just a single level? Well, that's something you know from your quantum statistical physics. That's nothing but the Fermi distribution. It's the Fermi function at that energy. So if we compute that, in principle, that's what we're expecting to see as a function of epsilon. So you can do that exercise for different temperatures. So beta is the inverse temperature. I define different green functions for those temperatures. And I fill a green function like this, 1 over I omega n minus epsilon. And I compute the density, g dot density. So this returns, in principle, green function are matrices. So I take the 0, 0 element and just keep the real part and put that in an array that I plot. That's what you see here. And you do recognize the Fermi-Dirac distribution here for different temperatures. At very low temperature, which means large beta, it's almost a step function with all energy below 0.05 here, which is my epsilon b, that are occupied. So this is almost 1. And as I increase temperature, there's excitations also at energies around it. And you see that this becomes, the step function becomes really this Fermi-Dirac distribution. So that's what you're expecting. Okay.
May I ask a question, please? In this code, instead of 100, I choose 10,000.
Oh yeah, well, okay, yes. So
and it gives very strange curve.
Yeah, no, I can imagine that this thing has some limits. What's happening? That's a very large number. So yeah. Okay. So the reason is most likely related to the fact that this beta appears in some exponential at some point, right? When you compute the Fermi function, or also when you compute the density, eventually you compute objects like e to the minus beta, this energy. And once you start filling numbers like that are this big, this probably leads to numerical instability. So for those kind of temperatures, I indeed suspect that you may run into troubles. Even 1000 is probably also quite low. Well, this one is still okay. But yeah, so that's a numerical instability. Of course,
so to speak, that the exponential of 10,000 is not really well defined. This is the problem, am I right?
Yes, exactly. I mean, if you ask NumPy to compute the exponential of this number, it will be quite unhappy.
Okay, thanks.
Michel?
Yes?
I have a question. So I was trying to plot that Green's function corresponding to flat 1.5. So, but it's showing some error.
Yes. So the way you have to do this, let me do it from here, maybe. Well, let me just try to do that for you. And I define a green function and I sort of fill it with a, say, flat. And I try to plot that object. So I can actually plot the spectral function associated to this. Okay, I'm getting an error too. Let me check where I made a mistake. Oh, sorry, this thing here. So that's what you get. So I define a green function. It has here. I didn't take a block one. I just took a 1 by 1. I initialize it with a flat density of states, and here I plot the associated spectral function. And as you see, this is a flat density of states from -1 to 1. If I had put 1.5 here, then you would have something that goes from -1.5 to 1.5. And you see it's normalized. So this number changes here because the integral of this has to be equal to 1. So just to make it easier, you see the integral would be 2 times 0.5. So indeed, this is a normalized density of states as expected.
Thanks.
Okay, this number 3 is just to give you a bit of intuition of the Matsubara frequencies. So here we define green functions on the Matsubara axis in those Matsubara frequencies I omega n. Here I initialize a very simple one, which is 1 over I omega n. And this is the sort of things that will come out of a numerical calculation, like using those quantum impurity solver. So you see, they're not quite as, it takes a bit of a habit and to actually interpret a function like this, because that's, what do I learn from this? And one of the goals here is to sort of get an intuition about that. So you see, that's for a temperature beta or temperature 1 over 10. And of course, the spacing between Matsubara frequencies depends on the temperature. If you remember the definition of Matsubara frequencies, they go like 2n+1 times pi over beta. So if beta increases, the spacing between Matsubara frequencies becomes smaller. And so this is why you get more point as you increase the number of beta points, right? Now, an important property is that if I try to extrapolate the imaginary part of G to 0, there's no point exactly at 0, right? The first Matsubara frequency is at pi over beta, so it's shifted a bit. But if I were to extrapolate this to I omega n goes to 0, I would get G at omega equal to 0. And this is where both the Matsubara axis and the real axis cross. And so I get some information about the value of the spectral function at omega equals 0. So this can tell me something about whether I have excitations in my system at omega 0 or not. Okay. So in this case, I definitely have a finite spectral density at 0.
Michel, sorry, where are blue and orange lines?
Oh yeah, they're hidden. So in that case, the guys are on top of each other. So that's why you don't see it. But so let me, I can't really change this easily, I suppose. Yeah, you're not going to see them because they're really on top here. If you want, there's 2 blocks. G has a block up, which looks like this. And it has a down block, but in that case, up and down are the same. So if I plot the down at the same time, you see they're on top. There's both the dotted and the other ones. So they're exactly identical. This is why you were not seeing them. They were just on top of each other. All right, here nothing really new. This is the explicit expression here for a green function for an isolated Hubbard atom. So this is just one site with a Coulomb repulsion, but no bath. I mean, it's just one site. This can be solved again exactly, and that's the green function, an associated self-energy. So if you use Dyson's equation and extract the self-energy, you'll find that the self-energy for the Hubbard atom is something that looks like this. And so you can try to plot it, and you see it's something that looks similar to what we were looking at before. But this time, this is the self-energy. So the self-energy is just a green function in a sense. In terms of its structure, it's also a green function. It has the same sort of properties. It has a different name, but it can definitely be described by a green function object, numerically speaking. This one is actually quite important. And you don't have to understand exactly where this comes from, but if you do second order perturbation theory for the self-energy, that's what you get. If you want this, there's a single Feynman diagram for the self-energy at second order in U. And the value of this Feynman diagram, you can show that it's this integral over imaginary time of a G0 tau cubed. And this is basically the Fourier transform. Okay? And so this is sometimes an approximation that we use. We approximate the self-energy by this second order perturbation theory. So it's useful. So how can one do this in practice? So you define a G0, which is your non-interacting G that comes here. You initialize it. So this is done, where is it? Here as a semicircular. So I initialize it in frequencies. And then I want to get, this is in omega, I want to get it in time. So I Fourier transform it. So this is G0 of t, is the Fourier transform of that object. And then to compute sigma, I multiply those G0t 3 times, because that's a G0 to the power 3. And I take the Fourier transform, which is what I do here. I Fourier transform, and I get a self-energy in frequency, which is that object here. So those 3 lines basically do the job. And you see this Fourier does all the job of taking care of how to do the Fourier transform, which can be sometimes a bit tricky. And once you have the self-energy, you can compute a green function and get the associated plot for the green function. So this will be something that is useful for the next notebook. And to see a bit, to have an intuition of how well or bad this second order perturbation theory is doing, you can actually start from this. This is the green function you see in I omega n. And as I told you, I mean, getting intuition out of this is not so easy. I mean, this is along the imaginary frequency axis. You know, I would prefer to have a spectral function. But this is an analytical, this has no numerical noise. I mean, it has a tiny bit of numerical noise because of the finite precision of the computer, but except for that, I mean, this is extremely accurate. And in that special case, one can do this analytical continuation when the data is so clean and try to go from the Matsubara axis to the real axis and extract the spectral function. And there's different ways to do this, but one that I use here is called using Padé approximants, and I'll skip the details of how this is done. But basically, you can use that function set from Padé, which does the job. So you define a real frequency green function GR, and to initialize it, you say, okay, for GR, I want to set it from Padé approximants that start from G omega. And GW here is what I had obtained earlier. And then I have, if this Padé transformation works well, I can plot its spectral function. And that's what I obtained. So you see, by doing second order perturbation theory, I started from a semicircular G0 with no interaction. This is this guy. And then I've put some self-energy effects in my system at second order and obtained the interacting function, which is this blue one here. And you see, you start seeing quite a lot of structure. So there's a narrowing of the peak here close to 0. Which corresponds to an excitation close to 0, a quasi-particle excitation. And there's a signal of something going on, coming here, those bands here, which you will see have something to do with the Hubbard bands in the Mott transition, and I'll come back to that later. Okay, that's that.
I would have a question regarding this plot.
Yes.
If you look at the second order result for the spectral function, you have this kind of kinks at omega minus
Yes.
1 and 1. Because I remember once in my master's studies, I did some calculations that had kind of the same structure that I had at, let's say, integer values of omega, always this kind of kinks. Do you have any explanation for this behavior, or is it just...
Okay, here
Yeah.
those kinks have, okay, they happen to be at integer values of omega. Not that much because it's an integer value of omega, but the reason is that this is where the non-interacting bath has a discontinuity in its derivative. So you see the bath is a semicircular, and the density of states is not continuous here. I mean, the derivative is not continuous. And because of that, it's propagating a bit of that in the solution here. So if you had a smooth non-interacting G0, which would not have this kink in its derivative, you would not have this structure here. It would be completely smooth. So that's an artifact of having this discontinuous derivative of the spectral function here of this semicircular.
Okay.
But in an interacting system, this typically disappears because for a realistic system, there's never such a thing as a discontinuity in the derivative. It's always smooth. And so those things tend to disappear.
Okay, thank you.
I have a question.
Yes.
So at zero temperature, one does not need actually to perform body approximation, right? Or no, or yes?
Well, okay. No, you still need, in principle, to do it. Of course, if you want the equilibrium formalism, the Matsubara frequency formalism is not very well suited for zero temperature. If you think of the Matsubara frequencies, they're spaced by something like pi divided by beta. Zero temperature is beta goes to infinity, so that brings your Matsubara frequencies, they become continuous. And the formalism is not really adapted for that limit. Even if, so you can, instead of say, I have exactly zero temperature, you could imagine that you have an extremely large beta. You'd get very dense Matsubara frequencies, but this would not buy you the analytical continuation. You would still have to do it because you get a dense mesh, but you get it on the vertical axis and you still have to project it to the other one. So typically at zero temperature, you don't use this formalism, but either the real-time one or something that is more adapted for zero temperature. And in those techniques, actually, in general, you get the spectral function for free. But there are different approaches, and you typically don't use the kind of quantum Monte Carlo that we will be using today for zero temperature.
Mm-hmm. Okay, thank you.
That was actually a comment that was made, I think it was Nicolas on Wednesday. Of course, according to the regime you're interested in, you may want to use different techniques and different solvers. And at zero temperature, there's other tools which are really good, like NRG, the numerical normalization groups, or DMRG, and other methods like this that are sort of based on diagonalization or wave function based methods that are more adapted for this limit. Okay. I know this is probably going fast for some of you that have just started the notebooks, but I still want to make sure we can discuss this one. I think it's probably the most important notebook, as it really is a first opportunity to really see the mod transition as it appears in DMFT. So this notebook is one in which we're trying to solve the impurity problem that appears in DMFT, but by an approximate method, which is basically second order perturbation theory. So we don't solve it exactly, but on the good side, what we will get is essentially an analytical result or semi-analytical with no numerical noise, and we'll be able to do the analytical continuation. So we basically start from the formula we had before, which is the second order perturbation theory expression for the self-energy. In general, it has a constant part, which is U/2, and then the dynamic part here, which is frequency dependent. This U/2 can be absorbed in the chemical potential, so we won't have to deal with that term. We just have to look at this at this term here. So what we sort of want is a class or something that allows to solve the impurity problem. And the question is, what are the inputs that we need? So what is the necessary information that has to be given to your, if you had a black box impurity solver? Well, basically what you need, and you can just tell it from looking at what you have here, what you need is, of course, the value of the interaction. You need to know what is the interaction, the Coulomb interaction on the impurity. And you need to know the structure of the bath that your impurity is connected to. And that is entirely encoded into G0, the non-interacting green function of the impurity, as we've discussed during the lecture. If I know this G0, I can extract delta as well, and delta has all the information about the bath. Okay. So you see, those are going to be the inputs. So you typically want to define a function that would be called solve and takes as an input U, G0, and you also need the temperature, as you can see from this integral or inverse temperature. You can be a bit more elegant if you want and wrap this into a class, say an IPT solver class, which you would initialize with the temperature. Then it would have a member G0 that you call or initialize at the moment after the solver has been instantiated, and then you call the solve method with the value of U, which then solves the problem. So this is how it's implemented here, and everything is quite trivial, the different steps. So at construction, I just give the inverse temperature, and this allows me to define the different members of the class, the different relevant objects for this, which are the interacting Green's function, self.g, which is an imaginary frequency green function at temperature beta. There's a G0, which is the non-interacting one, which is just the same structure, and a self-energy sigma. Then we will have to Fourier transform as before between frequency and time. So I need a counterpart. I need a time-dependent counterpart of G0 and sigma. So those are GF, but in imaginary time, right? And same thing for the self-energy. So those are all prepared at the moment when I instantiate my class, when I create my object. Then I suppose that the user gives me a G0, and then I solve the problem. Those are the exact same 3 steps as we've seen just before. I Fourier transform the G0 that was provided or initialized by the user into a G0 of t. This is used to compute G0 of t cube to the power 3 times U/2. This is exactly this formula here, G0 t to the 3 with U squared. And then I Fourier transform this object to get the self-energy in frequency. And then if I want to compute the green function for my model, I remember the Dyson equation, which relates G, sigma, and G0. And so this is what it is. It's saying that G is 1 over the inverse of G0 minus sigma. So that's my class. Now I've found a way to solve the impurity problem. Now I want to actually do DMFT, right? I need to implement those DMFT equations. And as you remember, they take a very simple form for the Bethe lattice because it avoids having to sum over K. So in that special case of the Bethe lattice, the DMFT self-consistency just reads like this. It says that the non-interacting G0 of the impurity is I omega n plus mu minus t squared, the green function of the impurity. Okay, so that's the special case of the Bethe lattice. How do we solve this in practice? We start with a guess for G0 and U is given. I call the impurity solver, I get a G, and I get a new G0 through this equation. I found a G, and from the self-consistency equation, I get a new G0. I have it, and I feed it in the impurity solver, and I loop. Okay, so you see it's very simple to implement in the case of the Bethe lattice. Okay, so of course it takes a certain number of loops. One could be careful and check exactly when it's converged. In practice, we can just take here, say 25 loops, and this is in general enough to converge the equation. So I give you a set of parameters and implemented this for one particular value of U. So I take U4, beta 1 over, temperature 1 over 20, 25 loops. I create an IPT solver instance. This is the object that will solve the impurity solver. And I need some sort of guess for G. So I start with just a semicircular. And then I do the DMFT loop. And that first equation is the self-consistency equation that I just wrote above. G0 minus 1 is equal to this, is exactly what I'm writing here. G0 is the inverse of I omega n minus t squared S of G. That's my self-consistency. It provides a new G0, and then I solve the problem for the given value of U. And I use my set from Pade function to try to get the spectral function associated to this, and I loop. And that's what I obtain. You see, at the first iteration, I got this blue curve, and remember, it has this little kink we were discussing because of the bath. But now at the next iteration, the bath itself is updated and becomes this, essentially this blue function now, which is smooth. So at the next iterations, this kink will disappear because I don't have this discontinuity anymore. And as the thing converges, it goes to a smooth curve here. Great. So that's for one value of U. We can put that in a loop for different values of U. So there's nothing special in this script. It's the same as the other one, but it's been embedded in a loop over U. And what you see is that as you increase U, something very special happens. You start at low values of U from a spectral function. You have to think of this spectral function as the density of states, if you want, the local density of states of your system. So in the beginning, there's excitations everywhere at all energies. Your system is a metal. And actually, that's not very far from the original semicircular density of states that would be what you have at U equal to 0. But gradually, as you increase U, you start to see a lot of spectral weight redistribution in your system. And you typically get a structure that has two structures here and one structure in the middle. The structure in the middle is called the quasi-particle peak. It is describing a well-defined excitation at low energy. It means your system close to omega equals 0 has well-defined excitations. Those are, if you want, the quasi-particles, the well-defined excitations of your system. But those excitations, this peak becomes narrower and narrower, which means that the quasi-particle weight, or if you want, how good your quasi-particles are, becomes worse and worse. And slowly they disappear, and eventually you have a transition to a state that has no excitation at 0 anymore and has a gap. And this gap tells you there is no excitation at low energies anymore. If I want to excite my system, I need to put bigger energies, and basically what I have is an insulator. So I have a transition as a function of U, which goes from a good metal to a metal with quasi-particles which are having shorter and shorter lifetimes, and eventually go to a Mott insulator. And those two structures here are called the Hubbard bands. And if you want, they're a memory of the atomic limit. If I were to solve the atomic limit, just a single Hubbard atom without a bath or anything, what I would get is two delta peaks at plus and minus U over 2. That's basically what you get when you solve the atomic limit. And those two things are a remnants of this. If I go deep into the insulator, my sites become essentially decoupled, and I start to have a spectral function which develops a peak at plus minus U/2. So that's really the celebrated Mott transition, and it was first described in the 90s. And this is taken from the review of Gabi Kotlia, Antoine Georges, and others who were, at the time, this was a fairly challenging calculation, and this is what they obtained. And you see, we can now obtain this super easily in a couple of Python commands, which is pretty cool. All right, so I think that's the main message that of these different notebooks. That then things are going to be refined, and we use exact solvers and so on. But I think the main message I want to carry through is this phenomenon, and this is what DMFT has really achieved, is to get a good description of the Mott transition, especially one in which I focus on all energy scales. This is what's a bit tricky in the many-body formalism, or in the many-body problem, is especially this one. You're not interested in just what's happening at zero frequency, which has been the case before when, for example, people were interested in the Kondo problem. There, all the physics is really driven by what's happening at super low frequencies, small energies. So you were not caring so much about other energy scales. Here you want to capture at the same time the low energy physics and this quasi-particle peak, but at the same time two larger energy scales that are associated to the atomic physics. And that is really the challenge, and that is what is nicely captured by the DMFT equations. All right. Do you have any questions?
Michel, you're comparing with review of Antoine Georges. Do they give experimental results, or it's really the same mathematical procedure?
Also, so this comes from so this is not an experiment. Of course, this is exactly the same calculation. So this is a numerical calculation. Now, if you're asking whether there are experiments that give you exactly the same kind of features here, it's of course you need to this is for the Bethe lattice, so this is sort of a Mickey Mouse version of a solid. It doesn't have all the details of the band structure of a realistic solid. So if you really want to compare to experiments, you need to be a bit more clever in the way that you define your dispersion, and you should probably not use the Bethe lattice, but really go back to the original expression here and insert the dispersion of the actual lattice of your material. And actually, even more than this, in most cases, I mean, in almost all cases, materials have more than just one orbital, of course. And so if you want a realistic description, you want to also take care of other orbitals. And this is the subject of a connection between density functional theory tools that are really good at or that aim at giving you a description of how the different orbitals of the system behave, and DMFT, which introduces the physics of correlations. And so there's a tool which has been developed, which is called DMFT plus DFT, and there's many variations of it, which aims at exactly giving really quantitative results that can be compared with experiments. So of course, this Bethe lattice here, this is a bit too naive to be directly connected to experiments. But the Mott transition itself is seen in experiments. I'll show you this in another notebook. But of course, it's never in direct agreement with this kind of spectral function.
Okay, thanks.
I have another question, if I may.
Sure.
Yes, if I increase this value of U in this simulation up to, for example, 12, these two quite smooth Hubbard bands, they get a peaked structure and well, different complexity. I'm not really familiar with this system specifically, but I was wondering if there is an like another transition or some physical way to understand this further evolution.
No, so what should happen if you really take the very large U limit? This is a limit that we can sort of solve exactly. If you think U goes to infinity, basically it means you're hopping, or if you want T divided by U goes to 0. So where you're slowly going is you're slowly going to the atomic limit. So you're slowly going to the physics of just one site, which is correlated, and that is disconnected from all of its neighbors. And this is something that has a single peak, delta peak, at u/2. Okay. Now, is this captured by perturbation theory? The answer is no. I mean, perturbation theory only works so well. I mean, in principle, it's actually quite surprising that perturbation theory can describe this so well. And it's actually by pure accident. It's because the second order perturbation theory formula that we're using here, I mean, this should only be working for small u. But it so happens, and that's an accident of half filling, that by chance, when you use this in the large U limit, this actually gives you also sort of the correct answer for sigma. So by accident, it captures the large U limit not so bad. But anything in between, of course, is an approximation. So if you start seeing funny structures appearing at intermediate values of U before you reach the infinite U limit, I would say that this is most likely an artifact of not using, or at least it's not something you can trust. I mean, your solver here is not exact, so you cannot really trust this at all. Another thing is the Padé approximation also gives some noise that is not always physical. Well, here it's actually not so bad, but some of those structures are also an effect of trying to do the analytical continuation, which induces some noise. And as you increase U, you get more of those unphysical features appearing. So this may, if you do U12 and see funny things happening, it could also be a consequence of your Padé not being able to capture the thing right. So I would not take anything happening at U12 too seriously with this method. I mean, you need something, a better solver.
Okay, thank you.
Okay, we'll maybe discuss just two more notebooks, or especially one, the last one here. I don't think we'll have time to discuss it, but you can of course try to play with it later on. Again, as Alberto said, I mean, I will, of course, these notebooks will still be online. So if you want to continue or try them another time, they'll still be available. The next two notebooks are basically about trying to study that mode transition, but this time not using the IPT approximation, but an actual exact or numerically exact solver. And one of them is the interaction expansion continuous time quantum Monte Carlo, which aims at solving this Anderson impurity model. And the notebook 6, there's not much in there really, except for instructions on how to use the solver. And in a sense, it works very much like the class that we have defined in the previous notebook. It's within the Trix CT_int module, and it has a member solver, which is the solver itself. And you initialize this with, again, the inverse temperature. And you also need to specify how many of those Matsubara frequencies you want. So it's a solver that will work in imaginary time and imaginary Matsubara frequencies. So you need to just tell how many of those frequencies you want to keep. So you instantiate a solver, initialize, just as we did in the other case, the non-interacting green function G0. And then you call the solve method that will solve the problem. But this time it's a Monte Carlo method. So unlike the IPT, it takes some parameters that describe how the Monte Carlo is performed. So the main parameters that control that, I mean, forget about this delta. This is not something I'll describe. It's something that allows to control the sign problem and improve it possibly. But the ones that control the Monte Carlo are these three. The main one I would say is the number of cycles. This n cycles tells you how many measurements you're going to do in your calculation. So this is how many times during during the generation of Monte Carlo configurations, how many times you will measure your green function or the object that you're interested in. So the larger this number, the better your statistics and the smaller your numerical error bars. Length of a cycle tells you how many steps you're doing between two measurements. So typically when you do Monte Carlo, you only make small changes at a time. And so if you measure all the time, configurations are very correlated. And in a sense, it doesn't bring more information to measure all the time. And the measurement itself can take a bit of time. So it's good to measure only after so many steps. So here typically 50 to decorrelate the different states. And the n warm-up cycles is how long you give your system or you give your Markov chain the time to reach equilibrium, which is something that you need to investigate how much you change it. But after some point, the results should not depend on how many warm-up cycles you do. So you execute that as an output of the solver as the GI omega contains the solution, the green function of your problem. Which in this case would give something like this with a real and an imaginary part along the Matsubara frequencies. You see, that's actually quite clean. So this is in a regime of fairly small u. Here the solver works quite well. And you see what you obtain is there's not a lot of numerical noise here. At least in the green function, you don't see it so much. Okay. I will skip this one, which is about the histogram of perturbation order. It's not too important. So the exercises here, I'll start maybe with the second one, which is maybe the more interesting, is an example where we compute both the green function, but then also extract the self-energy through the Dyson equation. Okay, so I'll do this again for the same sort of parameters as before, but what I want you to observe, and this is always the case, during the Monte Carlo, the noise in the green function is much smaller than in the self-energy. Those two contain the same information, but because the self-energy appears, if you want, as a ratio, I mean, G is something like 1 over something minus sigma, G in general has a lot less noise than the self-energy. And in the self-energy, you really see your statistical noise. This is for up and down for the two different species. In principle, they should be exactly the same. but you see there's a bit of numerical noise, and you can estimate your error bars as more or less the difference here between these two. And so by changing the number of measuring cycles, of measuring of this n cycle arguments that comes in the solve, you can increase or decrease your accuracy. And you see typically what you'll get here for the self-energy. Of course, if you only take 10,000 steps, you'll get this blue self-energy, which is very noisy. And as you increase the number of steps, you get more and more accurate data. And in statistical methods, the error bar grows down quite slowly. Unfortunately, it goes down like 1 over square root of the number of cycles. So if you want data that is 10 times more accurate, or that has error bars that are 10 times smaller, you will need to run it 100 times longer. So that's the effort. Okay, so this notebook is really about using how to use the impurity solver, and then we can go back to the mod transition and see, is there a difference between the solution we get between using an exact solver and using, for example, the IPT solver. And this has been done before, and this, I'll give you an example here from a publication where you have a description of the mod transition. So this axis is the temperature, and this one, the U, the correlation. And at low temperature, as I told you during the lecture, the mod transition is of first order. So you go from a metal to an insulator, and there's a region where you can in principle stabilize both solutions around the first order transition. And those two lines for the coexistence region, they gather into a critical point here where the phase transition is second order. And above this temperature, there's no true transition, but there's a crossover from your metallic state at small u to your insulating state. And you see, this is the comparison between NRG here, which is exact, and IPT, the iterated perturbation theory. And you see there's a bit of a difference there. Actually, IPT is not doing a bad job, but it's a tiny bit different. So we can try to reproduce this kind of, of course, it would take many, many runs, but at least to sort of observe this. And what you basically do is you rewrite the sort of DMFT loop that we had before. It's really exactly the same, with the one difference that this time, as a solver, we use the CTInt instead of our IPT solver. That's really the only difference. And I've run this for, so it takes a bit of time now. This is a statistical method. It takes a certain number of cycles. So if you do this for many values of u, you will see it can take some time. Typically, in practice, we would do this on a parallel machine. So we typically do these Monte Carlos on clusters, with 120 cores, and use the statistics from all of them to have better statistics and go faster. Here we have a single core on this server, so it takes a bit of time. So I scanned several values of u here, which took a bit of time. I launched this earlier this morning. And we can have a look at the result. Especially here, this is a plot of the green function that comes out of the solver for different values of u after having converged the DMFT equations. And you see, with a little bit of practice, you can actually recognize the mod transition by looking at those curves. It takes a bit of a habit. But by remembering that the extrapolation of those curves to zero frequency tells me what is the spectral weight at omega equal to 0, well, I can at least tell whether I'm sitting in a gap, in which case it extrapolates to 0, or if I'm sitting in something that has finite density that still has a quasi-particle peak. And you see the transition happens somewhere between U4 or maybe U4.5 and U5, right? So that's how you can read a green function along the Matsubara axis. You can also decide to use Dyson equation and look at the self-energy. And what happens in the self-energy instead is that it develops a peak around the mod transition. So up to values of U about 4.5, the self-energy is an object that still extrapolates to fairly small or smaller values here. But as you go to large values, it develops here a peak and sort of a divergence, which in practice is what destroys the quasi-particles. So it is this increase in the self-energy at low frequency that in this case destroys the quasi-particles. So this is sometimes used as a quantity to measure the quality of the quasi-particles. You take the self-energy and you measure its slope. if the thing goes to 0, it has a slope that is small, and by computing 1 minus that slope, you get something that is close to 1 for a good metal. And when this diverges, this becomes 1 divided by a large number, so that Z goes to 0. And you can associate or relate the Z to the weight that is inside this quasi-particle peak. So it is often something that we look at to describe the mode transition. We compute this Z by starting from the slope of the self-energy, and we plot this as a function of U. And it tells you, gives you an idea of what's happening. So here you see at small values of U, the quasi-particle P Z is not too far from 1, which means I have good quasi-particles, I have a good metal. As I increase U, this gradually goes down and eventually goes to 0, around between 4.5 and 5, where I reach an insulating state. I have no quasi-particles anymore. So this Z is often used as a simple scalar to describe the mode transition. So now we can, that's a pity, this is going to take some time. Anyway, I'll show you. We can actually compare the Z that we obtained within IPT with the one we obtained just now. Okay, so you can rerun the IPT, the iterated perturbation theory, and get the Z and compare versus CT int, and that's what you obtain. And you see, it's actually not so bad. I mean, here I have more points for CT int now, so well, let me try to just do that quickly. I don't need to run everything anymore. Okay, that's the plot with a bit more points now. So the blue curve is the IPT, which predicts a mode transition. You see at a slightly larger maybe value of U here, while the CT int, which is exact, predicts a transition maybe just a bit before. But you see, actually, IPT is not doing such a bad job at describing the mode transition. So it's funny that such a simple second order perturbation theory is giving you something very, very reasonable. And so just for the kicks, we can try, well, let's take this function, I mean, the result from the CT int, and let me try to do on that noisy data, Padé approximation. And, you know, that's the sort of things you get. I told you this is doing analytical continuation is something that is really difficult in practice and is not very stable, but sometimes it's halfway works, and here that it somehow works. At small values of U, you can still see that you sort of have a peak. As U increases, it becomes more narrow, and then at some point, there's no peak anymore. But you see the Padé has a real hard time to sort of describe what's happening at those energy scales correctly. And that's typical of Padé. It's very sensitive to numerical noise, and then at some point, it sort of gives random output. So if we want to get spectral function there, we have to use things that are a bit more sophisticated that Padé approximates, and there are tools like the maximum entropy method or other tools like this, which do maybe a tiny better job. All right, Michel, so that's what you get.
What is this negative peak at?
That's typically something that should not be there. So this is an accident of the Padé, which here is doing something crazy. So for this value of U, you'd see I'll change a tiny, so here I averaged over the last 5 iterations. Now let me average over the last 4 instead. And I get something quite different this time. This pink one that had a hole is now something different. So you see this all belongs to the sort of Padé approximation being very unstable against numerical noise. So it's a very delicate thing to do, and you cannot really trust. So all these features like this here is not real. So you can only trust very broad features like whether do I have something at low energy or not. Basically, that's how much information you can get from noisy data. All right. Well, I hope this gave you a bit of an idea of what the DMFT equations and the CT int solver can do and how they can help learn something about the mode transition. don't hesitate to come back on those Jupyter notebooks anytime. They will still be online. There's one more here about trying to stabilize both. I told you it's a first order transition, so in principle you can stabilize two solutions between these two values of u, and this is something that you can do with IPT and really see that you can stabilize in some interval of u two different solutions. So don't hesitate to come back, and also if at a later stage you have questions, you can always contact me on the Slack. I suppose this one will also remain alive for some time, or by email.
Michel, may I ask a question?
Yes.
I was wondering, so which kind of quantities can you actually compute from continuous time Monte Carlo? Since you're saying that basically to get real frequency information is kind of difficult. From the Matsubara, you can compute directly. You showed the quasi-particle peak. So what can you get in Monte Carlo simulations, also using more sophisticated approximants for
yeah, so I mean, if you have really good data, so for this kind of data that we're getting here, which is quite good quality data as here, if we were using Maxent as a way to do the analytical continuation, I think we would actually be able to get quite reasonable spectral functions. So that in that case would probably be possible. Of course, it always comes with some limitations. So at some point, as you increase U or lower temperature, the solver will not be able to get very good statistics and very small error bars. And at some point, the maximum entropy would also run into issues. But there are still many parameters or regimes where we can still use Maxent. Now, there are also quantities that you can obtain without having to go to the real frequency axis. And the best examples are all the quantities that are not directly real frequency dependent, that are integrated quantities. So of course you can get the average density of your system, for example, that is an integrated quantity. You can compute energies, so you can compute things like the kinetic and the potential energy of your system. You can also compute entropy. So all the integrated quantities are things that in general you can compute. Sorry? Sorry.
Oh yeah, it's not me. It's some noise in the room.
My bad. Yeah, so those are also things that you can get, and of course you can compute different correlators. So here, I mean, once you have your Monte Carlo running, you can compute correlators that are not your usual green function. So you can compute spin-spin correlators, for example. You can compute susceptibilities, spin susceptibilities, and things like that. And some of them require a Maxent. Some of them don't. If you're able to do Maxent, then you can compute conductivity and things like this. But there's still a number of things you can actually get even without having to do an analytical continuation.
Okay, so these are, let's say, the first things you would compute without Monte Carlo solver, and if you are looking at a new problem, probably it's the easiest things to do, right?
Yes, yes. You can get information from things like, the average value of the double occupancy, for example. The average value up and down will tell me whether I'm in a good metal or if I'm already in an insulating regime where I expect this to be very small. I can from Z, the quasi-particle peak, I can get information about the quality of my quasi-particle excitations. Yeah, so I would definitely first start from the integrated quantities and then try to do Maxent or something like this to go to the real frequency axis.
Okay, thank you.
Some more questions? Well, so I think if not,
there is maybe something on the chat.
Yeah, right, sorry. So Johan, you can maybe speak.
Okay, I see the question in chat, but it's maybe too vague for me to know exactly. There was a recent
Yes,
PRF on
maybe.
continuation.
Yeah, and you have to, but you can put it on the Slack. Okay,
Yeah,
and then when you find your citation, you can put it on the Slack, Jovan, and maybe Michel, you can answer.
Yeah, there's lots of. I mean, I'm mentioning some tools, but there's been it's a big activity, and analytical continuation here appears as a problem for getting range function and so on, but it's actually that very same problem appears in practical life all the time. So, for example, if you want to remove noise from a picture, this is also sort of an analytical continuation problem. So Maxent is actually used in those. You see it on TV when they want to get a target plate number and remove noise. I mean, these things can also be done with Maxent. So having efficient tools to do that would have applications that go far beyond the computing a spectral function.
All right. So I don't see any more comments or questions. So maybe
So I stop the recording.
we can stop now. Thank